Today we are going to do lecture number 20 in dynamics, and the topic of this lecture is from section 15.2 in your textbook, and the topic is general plane motion, and today we're specifically going to talk about velocity. So this is really a continuation of section 15.1. But when we talk about general plane motion velocity, what we really talk about is that idea that we talked about on lecture 19, where we add a linear and a rotational component. So in other words, if you have a deal like this, where you have a wheel that is rotating, you can, if you know the velocity, the translational velocity of one point, you can consider the motion of another point as being the translation of the first point plus the rotation of the point in question about the other point. So in other words, if we're going to look at a wheel rolling and we know the velocity of the wheel or the velocity of the center of the wheel, we can talk about the translational component of velocity as being the velocity of point A, and then we can just talk about the rotation of point B with respect to A, and adding those two together as vectors will produce the entirety of the motion. So some important points, and we'll talk about specifically how to do that, because the words are actually harder than doing it. So this actually follows very nicely from section 15.1. But general plane motion is neither a translation or a rotation. It is a combination of both. And general plane motion can be considered the sum of a translation and as a rotation. Just need to remember that that sum is a vector sum. So we need to consider the directions of those, the translation and the rotation. And the displacement of particle A and B to A2 and B2 can be divided into two parts: the translation and the rotation about the first point. So here on this slab we talk about point A rotating, and then we talk about B rotating about A. All right, so when we start breaking this down into vectors, we have to remember that since we're talking about a rotation of one point with respect to another point, that we're talking about a relative velocity. So we have an absolute velocity or a fixed reference frame velocity of one point, and then the relative velocity, which is the rotation of the second point with respect to the first. So, like we said, if you have A and B, and you want to know the velocity of B, if you can think about the velocity of A and then the rotational velocity of B with respect to A, add those two vectors and you'll have a complete expression for the velocity of B. So the velocity of B, just like we said, is equal to the velocity of A, which we're going to consider a pure translation in this case, plus the velocity of B with respect to A. So the velocity of A is just that, but the velocity of B with respect to B to A is going to be omega crossed with R, where R is the vector from B to A. So it's from the point that we're getting the absolute velocity of to the point that we're taking the rotation about. All right, so occasionally you can work that out without doing vectors, but it's been my experience that putting this into IJK form is the absolute best way to make this work. Okay? So, and then you can solve for any of those variables if you keep your vector stuff in mind. Now, these kind of sliding bars, this is another very classical problem that we do when we start introducing the idea of general plane motion. And this is the motion of A and B are not independent, are they? B is restrained to be purely vertical, and A is restrained to be purely horizontal. So if you knew the velocity of B, and you know the angle at this instant, right, of the vertical to B, you can say that the velocity of B is going to be equal to the velocity of A plus the relative or the rotational velocity of b with respect to a. So you literally think about this, let me put this up on the camera again, as being if you have this bar that's actually moving in this more complicated fashion, you think about the bar moving this way and then one point rotating about the other. Okay? And it's actually, it's pretty nifty, I guess is what I would say, the technical term for it. But it's a pretty nifty way to view it. So here they're doing it using triangles, which is not really my favorite way to do it. But on something like this, you can break it down. And this is a gear with a fixed bar and a moving bar. This is another kind of a classical problem. We're not going to do one like this. We may do one. There's another class of problems, or another way to view this class of problems. We may do one that looks like this later. But basically, we have a stationary lower rack, and then we have an upper rack that moves. And the question says the displacement of the gear center in one revolution is equal to the outer circumference. Which makes sense, right? If we're going around like that, that's going to move forward. If this is moving to the right, that's also going to move to the right. So we have a stationary gear down here, a stationary rack here. The gear moves, and the upper rack will move based on the rotation of that gear. Now, if you notice here, if this is a double gear, the upper rack is meshed with the inner gear. So we're really not interested in the larger outside gear, but the relative motion is going to be, the R value, in other words, is going to be, if we're taking this as a center, it's going to be from B to A, not to the outside, not to D. If we had something over there, we could talk about the motion of D as well. Anyway, so the angular velocity, we're looking for omega, and the velocity of the upper rack R, and then the point D. So in other words, the upper rack is going to depend on B to A, but D is going to depend on the larger gear, right? So those are sort of the parameters of the equation. So if we start talking about any point, the velocity of any point is going to be the velocity of that center A, plus the velocity of p with respect to a, which is omega crossed with r times the relative, the vector from whatever point we're discussing, whether it's b or d or a different point, to a. And as you notice also, if you think about it, since the gear, if we're rolling this way, the velocity of b, the rotational component, is going to add to the velocity of a, isn't it? But with d, it's just going to be going straight up at that instant. So that's why the vector piece comes in pretty handy when we're doing these. All right. So anyway, the displacement of the gear center is one rev of the outside, right? So if we rev this around once, then we can do that. We don't really have to mess too much with vectors except for just coming up with that value of omega. And since this is plane motion, since the whole thing takes place in the xy plane, we know that omega is in the z direction. It's going to either be positive or negative. And if you think about it from the point of view of the right-hand rule, this is a clockwise rotation, so it's going to be negative. All right. Now, here's a little bit more of a vector treatment, which is really the way I would recommend that you do these problems, just because it works kind of well every single time. So if we talk about the velocity of the upper rack, which is right here, we could say that that is equal to the velocity of b, because they're going to be the same, and that velocity of b is going to be equal to the velocity of a plus the rotation of b about point A. So we have the translational velocity here, and then we have omega crossed with r, which is 0.1 in the y direction, right? So we add that together, we come up with a k cross j is an I, and they actually just add together, which is what we sort of intuited in the beginning. Now for point D, it's a little bit different because the rotational velocity of D with respect to A is vertical or in the j direction. We have the same omega about point A, but we have a different moment arm. We're going from here to here in the I direction. And so we have an ij components, and we could find the magnitude of that and then just plot it back on the wheel. All right? So it's pretty clever. This is a little bit more complicated. We won't put anything like this on your homework or on your exam, but it's the same idea. We have a crank here from A to B, and we have a piston that is being moved over here. The motion of the piston, D, is restricted, isn't it? It has to be horizontal. So it says the crank AB has a constant clockwise angular velocity. That would be your omega. So it's a negative 2,000 RPM. RPM is revs per minute, so you have to put that into radians per second. And for this crank position indicated, we wanted to determine the angular velocity of the connecting rod B to D. And we also want to find the velocity of P. Well, another way you could set up this problem that might be, we know what this omega is. We might know what the velocity of P is. That would be something that you may know in that particular case. But working through the problem that way, when we start looking for the velocity of point D, we can think about it as being some sort of a translational velocity with some sort of a rotational velocity. And in this case, we can start from right here, which is where those two arms connect. And we can say that it's the velocity of B, which is not going to be purely x or y. It's going to have some sort of a component at that point, plus the velocity of D with respect to B. So we can find the omega and the velocity of B. And then we have to think about what the direction is. So once again, they break this down not using vectors. I would use IJ format absolutely on this, IJK. Anyway, then you can do a triangular solution and you can come up with the velocity of P, which we know has to be restricted to x. It's only in the I direction or in the x direction. And then we can back into the omega of BD, or the rotation of this second rod. So you kind of break that up into 2 or possibly even 4 problems. All right. Now, this is I don't want to go into this right now. We'll do this on the next section. The instantaneous center of rotation in plane motion is it's a geometric equation, not quite a trick, but it's a little bit of a way to analyze these problems in certain situations that make the math a whole lot easier so that you can get out of the vector stuff. I'm not a real fan of getting out of the vector stuff. You probably picked up on that already. Because the reason for that is just because if you stay rooted in good vector math, you're always going to be able to solve every problem, and you're not going to have to look for a trick. But sometimes if you find a trick, it can make your life a lot easier. So there's a balancing act there as well. All right, so to describe what's going on, I'm going to work problem 15.40 in your textbook. And 15.40 says we have a painter who is halfway up a 10-meter ladder. So that's a nice tall ladder. The bottom starts sliding out from under him. Very bad situation, right? But at that point, knowing that point A, right here, has a velocity of 2 meters per second. And once again, that velocity is restricted, isn't it? We can only move in the negative x direction. 2 meters per second directed to the left when theta, the angle that the ladder makes with the ground, is 60 degrees. Determine the angular velocity of the ladder and the velocity of the painter. Okay, so one thing, the velocity of the painter and the velocity at the top of the ladder are going to be different because we have a different moment arm, don't we, about that pivot. All right, so let's go ahead and draw a little picture here. We have the house, we have the ground, we have the ladder, and we know that the length of this is 10 meters, and we know this angle is 60 degrees. We also know that the velocity of point A is going to be minus 2 meters per second, and that's in the I direction. All right. So the painter is right here, halfway up, 5 meters. And this point B is at the wall at 10 meters. All right, so the first thing we want to do is to find the angular velocity of the ladder. So we want to find omega of AB, or BA. All right, so what do we know about this point B? Well, we can say that the velocity of B is going to equal the velocity of A plus the velocity of B with respect to A. Okay? And we know that this is minus 2I. And we can also, if we think about this as rotating around, it's a counterclockwise rotation, so we know that it's going to be positive, but we don't know what the value of that is. But we can say that the velocity of B is equal to negative 2I plus omega of the ladder crossed with, I guess it would be the vector BA, because that's going to be my R value, or A to B, I guess, is what I really want to do. Okay? So, if we look at this, we know that this is going to be 10, from A to B is going to be 10 times the cosine of 60 meters, and this is going to be 10 times the sine of 60. I said meters, but I meant degrees. And the cosine of 60, I think, is a half. I think it's irresponsible. So this is 5 meters. And the sine of 60 is 0.866. Multiply that by 10. So this is 8.66 meters. All right. So we can say then that the, and I should put a little thing there, that the velocity of B is going to be negative 2I plus omega, which is also a vector, and that's actually going to be in the k direction for sure, because everything else happens in the plane, times 5I plus 8.66J. All right, now right now we don't have enough information to solve the problem, except we know something about B. How is the motion of the ladder restricted? That is correct. B is going to go directly down. In other words, V sub B is going to be 0I. It's really going to be negative, but it's going to be plus something in the J direction. So if we take omega k and we cross it with this vector, what we'll get is, we could go I, jk, omega x, omega y, omega z, 5, 8.66, and 0. Right? All right, but what do we know about omega? It's purely z, right? So this is 0 and this is 0. So that simplifies our determinant quite a bit. So this is same sign, different sign, same sign, different sign. So I get minus omega z times ij, 5, and 8.66. Okay? And I should probably put omega crossed with r here, just so that I don't get confused. Okay? So I get minus omega times 8.66I minus 5j okay, and so this is minus 8.66 omega I plus 5 omega j. All right. All right, so then what I can do is I can break this up into the velocity, the summation of the velocity of b in the x direction is equal to 0, isn't it? Because in other words, b can't move in the x direction at all. So then I can just look at that piece of the equation, and I can say negative 2I minus 8.66 omega I. I don't really need my eyes. I'm just kind of doing that for, what would I say? Because, I don't know, because I want to make it reference it to this, definitely, to make sure that I'm talking about the I direction. And then I can say that the velocity of b in the y direction is not necessarily going to be equal to 0, but it's going to equal whatever that sums up to be. All right, so we have an I and a j. So here we just get, we don't even know what it is. The velocity of b in the y direction is equal to 5 omega. All right, so over here, I can solve for omega, right? Using this equation. And so I can, I've got a sign wrong here, this is bugging me. Negative 2 why are you negative in the I direction? I feel like that should be, it's positive. Why do I have this here? Oh, because it's negative here, right? Because we're going, well, it should be a positive. Plus, minus, same, minus, same, minus. Something wrong with that sign right there.
Is the 8.66 negative from the beginning?
That's what I'm trying to think of. Should I go negative and negative? Yeah, it's going to make everything work out. Is that a fair reason to do it? Yeah. If I go from B to A, I don't know why I did that, but B to A. There you go. Because we are, but see, the rotation is right here. The velocity of B with respect to A, so this is my pivot point, so down and down. Yeah, all right. So down, negative, over. Oh, I've got these two. I have these two mixed up. It's even worse than that, isn't it? No, it's fine. The 8.6 is J. Yeah, there we go. So negative and negative. So we go from B to A. There we go. All right, so that would make this negative. So I have a negative, negative, which is a positive, and this negative, 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 which makes that a negative. As highly unsatisfying to me. It's still going to be a positive. Why? That's what I can't. Oh, because this is negative, and this is negative. So if I go negative, this times this is negative times this is positive. See, I still think that's negative. I'm going to leave that alone for a minute because I want to finish up this. Okay, so if I do that, I get this value here, and then I get 8.66 omega equals 2, or omega equals 2 over 8.66, which is 0.231 to carry out an extra decimal point, and that's going to be in radians per second because I've got all my units dimensionless. Now, that makes sense to me because my rotation is counterclockwise, which is positive, so this should be positive. But I have something messed up in my signs over here. And it's just kind of bugging me.
Isn't the rotation clockwise?
Is it? So it should be negative.
If it's sliding down.
Yeah, it should be.
Yeah.
I have to go with that. There's just something I don't like about this. This is the correct value. It's clockwise, so it should be negative. So I think I was right to begin with. All right, so we're going to leave it like that. So we have a negative, if we're going to call it that, 0.231. So then forget what I said. What I had initially would have been correct with my sign convention. So basically, I want to rotate about this point, so my moment arm is going to be 5 and 8.66, and they're both positive. So that means this is plus and this is minus. Then when I multiply through, this is going to be a minus and this is going to be a plus. Okay, so I'm going to go back to my original thesis. All right, so then over here, I would have minus and minus. So this is a minus, this is a minus, and this is a minus. Okay, so there you go. Now, let's talk about the next part, which we've got that, then determine the angular velocity. All right, so to stick with the right-hand rule, it's definitely negative. It's definitely clockwise. All right, now what about P? What is the velocity of P? Well, the answer to that is the velocity of P is also the velocity of A plus the velocity of P with respect to A. But the painter is only halfway up on the ladder, right? So that means that this is going to be omega crossed with the R for the painter, which instead of being 5 meters in the x direction is 2.5, but I still want to do that. Boy, I'm just desperate to do that. B with respect to A, negative 5 in the x direction, and negative 4.33. So negative 2.5 I minus 4.33 J. All right, we still know the velocity of A, which is minus 2I, but now we also know omega, which is negative 0.231, and I can cross it with that. All right, so that means that the velocity of the painter then is going to be negative 2I. I'm going to do this determinant, ijk, omega, which is in the k direction, 0, 0, negative 0.231, and then negative 2.5, negative 4.33, and 0. All right, so same, different, same, different. So this becomes plus 0.231 times ij negative 2.5, negative 4.33, which is plus 0.231 times negative 4.33i minus a negative, which is plus 2.5j. All right. So then I get 0.231 times 4.33. So in the x direction, my I component is minus 1, and it's just 0.00023, so I'm not going to carry that out. So I have minus 1I plus 2.5 times 0.231 is plus 0.58J. Okay, and so this is my omega cross R. All right, so then the velocity of the painter expressed as a vector is negative 2I minus 1I plus 0.58J. So that is negative 3I plus 0.58J. And that is going to be in meters per second. Now, if there's just something funky about this sign. Negative. This is positive, so it's negative. Negative. All right. I don't know. There's something that's bugging me about this. But I can't see it right now. But no, I guess that makes sense. Because if P is moving down, that means the painter's also moving this way. So if the velocity here is 2, the x direction of the x component of the painter's velocity is going to have to be greater than 2, isn't it? Because he's moving in the same direction. He's moving to the left in the x direction. Okay. Otherwise, if he was rotating toward the wall, then there would not be a problem. We would not have to worry about him falling off. So, all right, so there you go. So, what is the speed? The magnitude of the velocity of the painter would be the square root of 3 squared plus 0.58 squared. So that's 9 plus 0.58 squared. Take the square root of that number, 3.05. So the speed with which he's moving is 3.05 meters per second. Okay. All right. And of course he would be moving, he's moving downward and he's moving to the left, which is what this, see do you see what's bugging me? I just feel like there's a sign problem here because I feel like the painter is clearly moving down. So why that's up is bugging me.
I think.
Tell me.
Happened.
Yes.
Is, it kind of seems like when you substituted it back into the equation, you maybe forgot to distribute the negative sign.
Oh, okay.
Because it's like should be negative 2y minus parentheses minus 1i plus 0.58j.
Thank you so much. Yes. That's going to make me so much happier. Thank you, AJ. All right. All right. So that's what some of my math colleagues will call an engineering solution. It's like where, you know, when you see the numbers like that and you're like, you look at the picture and you're just like, that's not. I mean, the numbers are telling me one thing, but when I'm looking at it, I'm seeing something else. So there we go. All right. So do you guys have any questions? All right. So that's it. We actually get out 20 minutes early today, if you can believe it. So that's it for section 15.2. We've got a homework problem. We'll do 15.3 on Friday and 15.4 on Monday. I also want to let you know I may not physically be here on Friday. I have to take my mom, who lives in Billings, to a doctor's appointment. We don't know when the doctor's appointment is on Friday. So if I'm not here, I will send you an email, and I will have a video for you about section 15.3. So, but yeah, so if you're not here, that's just fine, one way or the other. But like I said, I appreciate you coming. I appreciate your company. So, all right, well, that's it for today, and we will see you Friday, either in class or on Moodle. So have a great day, you guys.